Hi, I've received several questions about threading, or threads really, because we always talk about threading, but we don't talk about threads that much. So I thought I'd do a little quickie to help answer, I hope, some of those questions. So what are threads used for? Well, in a machine shop, there's 4 basic reasons for using a thread. And the first, well, is one that we're quite well acquainted with, and that's assembly. And we can see here a screw and nut assembly using a 60-degree V thread. Now, most assembly threads are 60-degree, but be careful. There's a few 55-degree threads kicking around out there. Why 60 degrees? Well, because it's a good mix of axial thrust and radial thrust. Now, what does that mean? Well, a 60-degree thread has 30-degree flanks, and a 30-degree flank that abuts up to a 30-degree flank on its opposing thread, well, pushes more axially, or pulls, than it does radially, but it still has some radial thrust and axial thrust, and that means that it will be easy to tighten down and will have a tendency to lock itself in place just a little bit, so it reduces the opportunity of loosening due to vibration. And that 60-degree is sort of a good mix for those two properties. Now, why not a 90-degree thread? Well, a 90-degree thread would have 45-degree flanks, and they would pull pretty well as much as they would push outwards. And well, that would make for a thread that would be harder to tighten down because it would want to wedge itself inside the opposing groove. Anything open more than 90 degrees, well, would just wedge itself. So really, 60 degrees is a good compromise for assembly threads. The second reason that motivates us to use threads, well, there's another one that we're quite used to, and that is mechanical advantage, as we can see here with this machine vise. Now, a light amount of force applied on the handle gives a large amount or a great force applied on the part. And how is that? Well, our thread changes rotary motion into linear motion. And to the rotary motion, I can add a lever. And that's what the handle on a vise does. It gives me leverage. So let's imagine that we have a very small vise, and that small vise has a 20 thread per inch screw on it. And that 20 thread per inch screw has a pitch of 0.05 inches. Why is that? Well, it's 20 threads per inch, so 1 inch divided by 20 is 0.05. That's the pitch of that thread. Now, if I put a handle on this vise that was 1 inch long, and I held the end of that handle and I turned 1 full turn, the end of that handle would travel somewhere around 6.2 inches. Why is that? Well, 1 inch times 2 for the diameter, and pi is 3.1416. So pi times 2 inches will give somewhere around 6.2 inches. And well, that means that when I turn 1 full turn, I move 6.2 or 6.25 inches. And that the thread advances 0.05 inches. That is a huge advantage. Actually, it's 125 to 1. Now, there is some friction involved, some radial thrust involved, so it's not completely an advantage. But it would be safe to say that we're getting about 90 to 100 times advantage here. And isn't it Archimedes that said, I'm not sure, but I think it's Archimedes, that said, well, if you give me a large enough lever, I can move the world. The third reason that would justify using a screw thread in the machine shop, well, is accurate motion or movement. And well, we see that all over the shop with our lead screws. If we want to move the table on a milling machine, well, we can move it very accurately because we can break down the pitch of a lead screw into degrees of motion and really just adjust how much movement actually we get quite accurately. And that's great, but it gives us both of the last two, the second and the third reason. That lead screw gives me a mechanical advantage, because moving that mill table would be very difficult by pushing on the table by hand. But it does give us the third reason, which is the accurate motion. And that's very important for everything we do around the shop. Now, mechanical advantage and accurate motion, threads usually, not always, but usually use a 29-degree V, which is an Acme thread. So 14.5 degrees per side, and that gives me a lot more thrust, axial thrust, than radial thrust. So they do not tend to want to bind in their hole, and they push quite positively on the table. So Acme threads, good for that. So if the axial thrust is a problem, why not just use a square thread? They used to be used a lot, and they aren't used much anymore. Well, for two reasons. They are very difficult to produce, especially in a mass production way. And also, well, they are difficult to produce because the tool is prisoner of its own groove. And that, well, makes for problems, especially when it comes time to grinding the threads if it's a hardened lead screw. So that 29-degree V, even though it's not a very pronounced V, makes for a groove that does not imprison its tool. And that means we can grind it and cut it a lot easier. The fourth reason for using a thread, well, is accurate measurement. And we know that a micrometer uses a very accurate thread to measure the amount of movement on the anvil here, to measure very accurately. And as a general rule, these very precise micrometer threads are 60-degree threads. So there you go. We have assembly, we have mechanical advantage, we have accurate movement, and we have accurate measurement. 4 reasons for using a thread. Now, how do threads work? Let's go take a look at that at the whiteboard. Well, here we have a representation of a 60-degree screw thread. Actually, what we have is a teaching aid that I've made up. Why? Because I have no life. Regardless, it is a representation of a 60-degree thread, and more specifically, a 60-degree unified thread. So what is a unified series thread? It's a thread that unites or unifies 3 different standards: American, Canadian, and British. And it came about in the late 40s, after the Second World War, where certain problems were encountered because of different standards in threads. And this was made up to alleviate or circumvent those problems. At first glance, they may seem to be mirror images, but they aren't. There's subtle differences. First off is the crest and roots. If we look at the crest of the internal thread, well, we see that it's wider than the crest of the external thread. And inversely, the root of the external thread is wider, and naturally so, because it has to go with the crest of the internal, so it's wider than the root of the internal thread. Now, in this case here, I haven't represented it properly because the roots of the internal thread here should all have a small radius on them. Whereas the roots of the external thread, well, can or cannot have a small radius. We have 2 forms possible, and that's because it's a unified system. So we accept in this system a small radius at the root of the external thread, or a flat at the root of the external thread. So close, but not quite the same. Another thing that's important to talk about, well, is terminology. And we saw a lot of terminology in our threading on the lathe video, so go take a look at that if you want to remind yourselves of those terms. However, there are a few terms that I want to run through here now, and that is root, crest, major diameter, and minor diameter, because they create a lot of confusion, and I see that in the questions that I receive. Now, the root of a thread is the bottom of the groove. The crest of the thread is the top of the groove. That means that the root of an internal thread is the bottom, and the root of the external thread is its bottom. That we can wrap our minds around. However, major and minor diameters. The major diameter of a thread is its largest diameter, whether it be external or internal. And the minor diameter of a thread is its smallest diameter, whether it's internal or external. So if we look at an external thread and we say, let's look at its major diameter. Well, I'm measuring the outside of that external thread. That's the major diameter. But if I measure the hole on an internal thread, I'm actually measuring the minor diameter of the thread. So you got to be careful with that. Another term that creates a lot of confusion is nominal diameter. Now, it is important to know that threads have nominal diameters, but that the nominal diameter doesn't exist. If I have a 1-inch thread, it does not measure 1 inch. Its nominal diameter is 1 inch. But it doesn't measure 1 inch, because a 1-inch thread that would thread into a 1-inch thread, well, wouldn't fit. We need space between the crests and the roots to have a thread that assembles together. If we look in the handbook, we can see that for a 1/2 inch 13 UNC class 2A thread, our major diameter is somewhere between 498 thousandths of an inch and 487 thousandths of an inch. Now, I don't think anyone would want to have to name or call this thread a 498 to 487 thousandths of an inch 13 UNC thread. No, it's a lot easier just to call it a 1/2 inch 13 and say that 1/2 inch is the nominal diameter. The actual major diameter, well, that'll depend on the class of fit that I want. Another term that I hear quite often is sharp V threads, and that needs to be clarified. Now, our thread form here has either a rounded root or a flattened root. Round or standard root. That's what exists, and that's what's possible. But we could have, and we see it here, a V that comes to a point, and that would be a sharp V thread. And that doesn't exist in reality. You cannot cut a sharp V thread because a perfectly pointy tool has no surface on its end and could not lift a chip there, so it would just tear. It just doesn't work. Plus, it creates a focal point for stress that would really help a thread to crack rapidly or to fail prematurely. It just doesn't exist. So why do we talk about sharp V threads so much? Well, because sharp V threads are important for calculating. If we want to know where the radius should be on the root or where the flat should be, well, we know where it should be from the sharp V point, but it is really just something we use for calculations. Another question I get quite often is, well, what's going on with fine series and coarse series threads? Well, yeah, what is going on with that? Well, one is fine and one is coarse. But why would I choose one over the other? Well, let's take an example. 1/2 inch 13, 1/2 inch 20. So we have a fine and a coarse series threads. Now sometimes there's special series as well, but there is always a fine and a coarse series. So why one? Why not the other? Well, if you have a coarse thread, in this case a 1/2 inch 13, well, that means that the V is going to be much larger than the V on a 1/2 inch 20 thread. That's normal. I have to fit 20 threads in 1 inch of distance. whereas a 1/2 inch 13 only fits 13. The V's are going to be a lot larger. And that has many advantages. Ease of assembly is one. Reduced risk of cross-threading is another. And reduced shear on the thread itself. However, the coarse thread has a much weaker core. That means the diameter of the thread between one root and its opposing root. If the V's are larger, they're deeper, and that means that there's less meat in the middle. So if the strength of the screw itself is something that needs to be considered, well, a fine thread will help with that. But it's not just that. There must be something else, because that would make much ado about not very much. And well, there is, and that's vibration. We mentioned, or I mentioned earlier on, that the 60-degree V was sort of a good compromise between axial thrust and radial thrust. So I'd get mostly axial and a little radial that would lock the thread in. That was a 60-degree. But for vibration, I want the thread to sit and lock easily. And other than using a flathead screw that are made to reduce vibration problems, they really are made to lock in. The head locks, that's the flathead screws. Well, other than using those, a fine thread is what's normally called for. And why? It's a question of helix angle. Now, if I have a 1/2 inch 13 thread, the helix angle is quite pronounced. And if I have a 1/2 inch 20 thread, the helix angle tends much more, but never gets there, but tends towards 90 degrees. So, more helix angle, less helix angle. What do you think? More helix angle is going to make a thread that is more prone to loosen by vibration. It's easier to unscrew. Whereas less helical angle makes for a thread that's a lot tighter and a lot less prone to loosen by vibration. So those are, I should say, important considerations when choosing fine or coarse series threads. I also get a lot of questions about metric threads. So let's debunk that a little bit. Metric threads and imperial threads really aren't all that different. They're basically the same. What are the differences between them? Well, one thing that's the same is the 60-degree thread. Isometric or unified series, it's 60 degrees. And 60 degrees in metric and imperial is 60 degrees. But what is different? Well, 3 things, major differences. And the first is obvious. All the dimensions for a metric thread are in metric, and that means millimeters. Whoa! Second major difference is the pitch. Now, in imperial threads, they like to give us a hard time. So they always call out the thread with a number of threads per inch. 1/2 inch, 13. Or here, we'll take 3/8, 16. Okay, a 3/8 16 is a thread that is quite popular. And its equivalent in metric is an M10 1 by 1.5. Now, 3/8 is the nominal dimension of the thread. It doesn't measure 3/8, but that would be its dimension if we went to a sharp V. So, 3/8 nominal. Great. In metric, M10, the M just means metric. 10 millimeters is its nominal diameter. Is it going to measure 10? No. You see, it's the same as in imperial. It doesn't measure 3/8. Well, it's not going to measure 10 millimeters. But it's going to be close. And what about the pitch? Well, in imperial, they give us 3/8 16. 16 isn't the pitch. It means 16 threads per inch. If I want the pitch, I have to divide the distance 1 inch by the number of threads, 16, to get the pitch. In metric, it's the same but totally different in that they don't screw us around, they give us the pitch right off the bat. In other words, M10 by 1.5 means it's a 10 millimeter diameter, nominal, and its pitch is 1.5. That means that it will go around the part, or each time you make one full revolution, the part will advance 1.5 millimeters. As you see, it's the same. The pitch in metric and imperial, it's the same logic. It's just that in imperial, they give it to us in threads per inch to start, and they force us to calculate it. So, no big deal there. And what is the third major difference? Well, the third major difference is how the fits are classified. Now, we'll take a few seconds and just introduce the notion of fits in imperial, and then we'll move on to our next video eventually, part 2 of this thread talk video, where we're going to be looking in great detail at fit classifications for threads, both metric and imperial. So let's introduce the notion of thread classes. So as things sit here, we have very little clearance on the flanks of the threads, and it's the flanks that count to ensure that we have a good assembly, or the required assembly, I should say. So as we look here, we see there's very little clearance along the flanks between the external and the internal gears, external and internal threads here. But don't worry, we have a lot of clearance on the crests and roots, and that's fine. This is a representation of a class 3 thread fit. Oddly enough, a class 3, because there's 3 classes, is the one that has the least amount of play. And that would mean from 0 play to just a very little bit of play. So if we look now at a class 2, we see that we get a little more play here. And finally a class 3, where we have a lot more play. Now you may have noticed as we cycled through the different assembly classifications from a level 3 to a level 1, 3 being the tightest and 1 being the loosest, well, that the bottom or the external thread here is the one that moved. The internal thread never did move, and that's because thread classification is a hole-based system. And what does that mean? Well, we'll have to talk about that in our next video. And please come back for the next one. I know this stuff is about as exciting as watching a lake freeze over, but it is important. So until we meet again, have fun, be safe, and happy machining.
So all I ever wanted was a little monkey from you.